Good morning from Oslo. Welcome to this webinar that we're going to go through here in the next 30 to 45 minutes. This is the first webinar in a series that we are going to drive over going forward, where we will pick subjects that we believe are important to our customers and share that insights in this format. Everyone who is a registered user at radiocrafts.com will get an invite of this, so stay tuned for the invites that are coming up. I'm happy to see here that we are over 100 people actually register for this webinar, so it's a pleasure that we are attracting that many people, and we hope that we can bring you value over this webinar and this series. Presenters today is later, who is the main attraction for the day, is Ørjan Nottveit, who is our R&D Director. He will share the technical insights here in the 169 megahertz antenna design and tuning. Behind the scenes today is Neris Akaukaus, our sales manager, who is controlling the chat window and all the technicalities. And then there's me, Anders Oldebeck, Sales and Marketing Director of Radiocrafts. In terms of questions and answers, please post those in the chat window as we go along. Me and Neris will respond as much as we can in real time, and we will also have a session after the webinar where Ørjan will also be able to respond to the more technical questions. That will be for 5 to 10 minutes, depending on the amount of questions that we get in. There will also be, at the end of the seminar, you will get an offer for a development kit, so stay tuned for that one as well. So with that short introduction, then let's get into the webinar. And first I will give you a short introduction to Radiocrafts. So for those who haven't been so much involved with us, we are a company, we are devoted to short development time with proven quality. The company was founded back in 2003 in Oslo, Norway, where we still are. The founders are Peter Martin-Ebben, who is still the CEO of the company, and Halvard Moholt, who was co-founder at that point, who still has one seat in the board of Radiocrafts. What we do is basically very compact surface mount modules, RF modules with embedded radio protocol. What we try to do here is to get as efficient development time as possible for our customers and to combine that with a low-cost manufacturer. You will find on our website and in our offering a complete suite of tools and also online support. So we try to be as much of help as we can for our customers to get to the market very, very quickly. We have millions of modules out in the field already. The return rate is not public, but it's very low. We cannot afford to keep that high. So you will get high quality modules. We have a global distribution network that you also can find on our website. We do our manufacturing in the Baltics, where the costs are a little bit lower than Norway. Norway is great in many, many respects, but due to the economy of Norway, manufacturing might not be the best place in this country. We are members of the Wireless M-Bus Working Group in the OMS and in the CEN, members of KNX, and member of Texas Instruments Third-Party Network. Next slide. Yeah, thanks. What we do, talked a little bit about that, support short development time with proven quality. That means that we do as much as we can to pre-certify our modules. You will not need to do that much in terms of design work. We will do a lot of that for you. Our modules are in general configurable. That means that there's no need for doing embedded programming as such. You need to configure the behavior of the module, but that's it. It's typically done in 1 or 2 weeks rather than months, several months for the programming. We have multiple wireless protocols. Really, that gives you the optimum choice to find the balance between cost and performance for your requirements in terms of RF. The development tools I talked about. We also have some hardware boosters. You can find those on our website. The antenna tuning is kind of an example of that. We bring out some good stuff for you to use to increase the system performance. Encryption, of course, the antenna design, as we're going to talk about today. And they are surface mounted, and all of our modules going out are RF tested, so you will get functional modules also in volume production. Thank you. So for today, we're going to focus on 169. It is available as a license-free band in all of Europe, which is a change in the last few years. Earlier it was open only for the utilities, but that is a change. So now it's open for anyone with some certain restrictions, of course, as normal, but you can put any type of equipment out there talking on the 169 megahertz. The good thing with that is that you get a fantastic range for narrowband application. We did tests in Oslo ourselves with the commercial antenna and our development tool. And we did physically walk 3.5 kilometers inside of downtown Oslo before we lost the connection. So the 3.5 kilometers, that's not a marketing number, that's a actual number in a real city environment in Oslo. You can see the details on that in the app note that is mentioned here, app note number 21, which is available from the website. With that range, you can build low power WAN networks. They will cover 40 square kilometers with one RF module. So it gives you, we bring out these numbers just to give a perspective what can be done with the 169 megahertz. It's actually a very, very powerful tool to use if you want to have coverage outdoor. We have a PC and obviously a PC and the Radiocrafts USB stick with the antenna. That is what you need to create your network, basically, and then the modules on the nodes. It is an alternative, we believe, very strong alternative to low power WAN networks such as Sigfox, LoRa, and narrowband IoT. All of them has their own benefits and drawbacks, but if you compare the networks for low power WAN, you should consider 169 in that comparison. Many gas and water meter companies around Europe are already using this. As I mentioned earlier, that was the first application of 169 megahertz. So it is tested already in the market, and it's not a novelty as a technology. The new thing is that it's available for people outside of the utilities. You will see the announcements coming up of something called the WISE Alliance. I'm not sure that that is widely known by now, but that is a organization that has worked a lot with 169 and is now taking that knowledge and bringing it out more towards general type of customers. So you will, if you Google on WISE Alliance, you will see what that is, and we are part of that, of course, and so we see that this is a start for the 169 megahertz as a true alternative in the low power WAN market. So the challenge in 169, if everything is so good, what is the problem? You might call it a problem, but the antenna, because of the wavelength of 169, it means that the antenna is bigger than it is for other ISM band frequencies. So it can be a challenge. You can simulate, analyze, and you can do all these theoretical modeling and you can have all the tools, and you can read all the textbooks here, and you can calculate all this thing and get the theoretical things very, very right. We can ask a company, an RF specialist company, to do this. But as we have been through this many, many times, we found that there is a very, very easy path to resolve the antenna issues, where you don't really need to understand all the RF theories behind, but we have created a working model that actually does just that. It works. It's proven by hundreds of thousands of antennas out there in the market that is working today. So with that, I will leave the word to Ørjan to share some of the secrets behind that. So Ørjan, please.
Thank you very much, Anders. Yes, so as Anders mentioned, one thing which is often seen as the challenge in 169 is to make the antenna good. And the reason is, as Anders mentioned, the antenna size will scale inversely with the frequency. That means that a 169 MHz antenna will be, for the same antenna type, will be 5 times larger than an antenna at 868 MHz and 15 times larger than the same antenna at 2.4 GHz. So the antenna size scales, but the product rarely scales with it. So that means you have to, in comparison, make a much more smaller antenna at 169 than you have to do at the other frequencies. So also, as Anders mentioned, what we present here is not the only way to success. There are several ways. And the ideal way is, as Anders mentioned, to do theoretical studies, to do simulation. Basically, you would have to 3D simulate the entire product, not just the antenna, but the housing of the product, the PCB, the ground panel, all the ground plane in your product, all the components in the product, all the screws and stuff like that has to be modeled in. And this requires expensive tools. It requires a lot of time. And in the end, if you then change your product slightly, you have to do the whole thing all over again. In addition, this requires, as mentioned, a lot of knowledge. And we see that a lot of the people that want to do a 169 MHz design doesn't necessarily have the master in antenna design. So therefore, we offer an alternative path for non-antenna engineers to make a very good antenna solution, not a 100% best, but a very good one in a practical and easy way. So our path is a 5-step path. So first of all, it's to select an antenna and a position inside your product at an early stage. This is one of the key, and I cannot emphasize this strongly enough because I will talk more about that later. Then you choose an easy and well-known antenna structure. You use what is called the antenna tuning feature inside the Radiocrafts modules, which will enable you to test the antenna inside your environment. Then you will tune based on the principles that are outlined in this presentation. And then you will verify the results either with a simple range test, or you can go and do radiated power measurements in a radio chamber. So now I'll go through these 5 steps in a bit more detail. Plan the antenna design early. This is, as mentioned, a very important step, and I cannot emphasize it strongly enough. If you wait until the mechanical design is done, the PCB design is done, that means you will not have the room to make a very good antenna, and it will be a very challenging task. And it's also important to make enough room for the antenna, because size do matter. Do not try to make it too small. Do not try to make an 169 MHz solution in a 2x2 centimeter box. It will not be a good solution. So you have to make some room. And if you already have a complete product without antenna and want to put an antenna in later, I think that's almost an impossible task. A key is also to get the mechanical designers involved so that they understand that you do need the room for the antenna. The mechanical designers are often more interested in how things looks and the design of the product, and they do not always understand the importance of the antenna. So involve them. So this is more a general step, I would say. Simple antenna structure. Yeah, there are many advanced and fancy, I would say, antenna structures out there. You will find them from commercial suppliers and also as reference designs. The challenge with the advanced structure is that they could theoretically outperform a simple structure. However, it's very difficult to work with them. So that means if you take an advanced structure, like a 3-dimensional PFA antenna, then it's very difficult to work with it as your product will detune it. And advanced antenna structure will also be very easily detuned. So they do in a theoretical and in a reference design, they will probably outperform a simple one by some small dB or something, but it will not be a very good. We don't think that's a good solution for most customers to do. So antenna tuning, why do we have to do that? And this is, I guess, the key part of the presentation. Because when you take a reference design of an antenna, when you take a ready-made antenna from a commercial supplier and put it into your product, you will find that it does not behave as expected. And that's not because the antenna supplier lied or anything in the datasheet. Basically, it's because they have tested their antenna on their reference design, and it will behave differently in your product. The reason for these are many. One is that the ground plane of your product is different. It could be smaller. The antenna could be instead of in the reference design, the antenna might be in the center of the ground plane. In your design, it might be on the side. There's a different shape of your ground plane. You have the housing. Most reference design for antenna doesn't include a housing on top. Maybe you have some sort of antenna support, some plastic, which is making the antenna mechanical stable. Maybe you have some coating on your product. Maybe you have some potting. You might have screws and another fastener. So basically, all these features will make the antenna detuned inside your product. And what's the consequence of that? When you measure it, suddenly an antenna is significantly reduced performance compared to the reference design and what your expectations were. This, I'm sure that everybody who makes an antenna at 169 will meet this challenge. 100% everybody. So what to do? So we have made an antenna tuning feature, which consists of, I would say, 3 different parts. One is an embedded feature in our RF module, the RC1701HP MBUS 4. So basically, it's a separate test modes. So for those of you who know our modules, you will enter a configuration mode and select a certain test mode, which is called number 7 in this case. That will put the radio in a sweep mode. That means it will send burst packets covering a certain frequency area, and it will sweep this area 7 times. Then you will have to have a receiver. It could be a spectrum analyzer for those that have it. For those who does not have that type of RF equipment, they can also use things like a EIRP or other like low-cost PC-based spectrum analyzer or software-defined radios, as they're often called. So it doesn't have to be an instrument that costs 50,000 euro you have to make. Sometimes you can do it with a much more easy solution. And you will also use something called the max hold settings, and you will basically set the device to cover 5 megahertz. I will show you just soon how the results will look like. The final thing you need is a stable measurement setup. You do not need to be in a radio chamber, but you do need a controlled environment so that you can repeat the measurement over and over again. So that means you have to have a desk or something where you have the device on a test at a certain position and the receiver at a certain position, so that you can repeat the basically same test setup one day after another. And also we do recommend that you can use our development kit or our development board as also a reference design, so you can also test that device in your test setup. What that will give you is that it will give you a known device with a known radiated power, so that will help you in seeing the absolute values of your antenna design, which could be very useful at the tuning process. So when you use this internal feature and when you use the receiver, you will end up getting a result like this. This shows at 169 megahertz a span of 5 megahertz here, and we see how the antenna radiated power differentiate between or varies over the frequency area. And this is kind of the key measurement you will use to evaluate as you tune. The key here is this orange line, which is kind of the envelope, which is what you want to read out of this. So the envelope has, of course, some key features. One is where is the peak frequency? What's the optimum frequency for this antenna? And also how wide is the envelope? Is it kind of very narrow? That's not good. But if it's wide, that's good. And also the height of the absolute height of this envelope. It gives you a number of the radiated power. So how does this work? So we have defined a process, which is let's say a two-step process of tuning the antenna, which we see that it works basically every time. One is changing the length of the antenna, and here comes the easiness of the simple structure. So a simple structure of the antenna is for us a quarter wave antenna. That means it's and 169. It's typically made as a helical antenna. So that is what you will see in our. We have a white paper which explains exactly what antenna to select. So I will reference that at the end. So when you have a simple antenna structure, like a quarter wave, either a straight wire or a helical antenna, that means that adjusting the length of the wire or a PCB trace, in case you make it on a PCB, will directly tune the antenna. So if you then have these results in the beginning, meaning here you have an antenna which works well at 167 megahertz, but not that well at 169, then you would have to make the antenna shorter in order to get the center frequency higher. So that means making antenna shorter will basically shift the curve like this. So the idea here is you cut the antenna wire, you measure, you cut, you measure. And then you will see it moving like this, and that will give you an idea what the ideal length of your antenna in your product is. On the same way, if you start with this antenna, you see that this is resonating at two high frequencies, so you want to make it longer, and then you will drift the center frequency downward. So that's the first step. And the second step of the antenna, after you've tuned the right resonance frequency of the antenna, then you have the matching. And here again comes the advantage of having a simple structure, because with a simple antenna structure, it is more easy to predict how the antenna match should look like. If you make a very advanced structure, it's much more difficult to say something, how it would work. Again, with a helical antenna, well, first of all, we do recommend that you put in a pi network for matching the antenna. So that means there are room for 3 passive components. We do recommend that you make these large in size, specifically at 169 MHz, because having small inductors at 169 MHz will make you lose several dB of efficiency. So we do recommend do not try to save space on using like 0402 or 201 components. Use them big. With a helical antenna, we normally see that just tuning the one component, which is called L1, is what you need. That means C1 is basically a short circuit. And we do see that by having a helical on a ground plane vertical, you will have to tune that L1 frequencies, L1 between in the range of 100 to 10 to 100 nanohenry. So that means you're very limited to the freedom, and that will make it more easy. Instead of trying to tune 3 different components, you basically have to tune one component. The antenna matching, when you measure it again, going back to your measurement setup, you will see that this is a very poorly matched antenna. You see the radiated power is very low, and you will see when you shift the values of these that it will go up and it will go down. So you will see a peak value at somewhere along this 10 to 100 nanohenry, and that is kind of your ideal matching inductor. Also here you see that when you do this matching inductor, we did see that the frequency also changed on these measurements, so the peak frequency. That means that it might be that after you have done this optimal tuning of the matching, you have to go back and adjust the length again, the first step. So this is kind of our process, which we suggest for the antenna design. You make an initial antenna design. There are reference designs both on our website and also on the on other websites you can Google. So you will find a good starting point. You put the device in your product. You measure, you evaluate, and adjust. And in the first iterations, you adjust the antenna length. That having a helical, just cutting with the pliers. Cut-ins in steps that start in small steps and go to larger if you need to. Cut, measure, cut, measure. Or in sometimes you have to extend it as well. When you find the right resonance frequency, you go for the matching, which basically is a one component match. You match, you measure, you match, you measure. And at the end, it might be that you have to go back to adjusting the length slightly again after the matching. And then you end up with something you need to do a verification on it at the end. And that's typically done either in case you're concerned about the distances you can get. You will do this by measuring actually on an open area distance. Or you can actually then go and have an hour or two in a radio chamber and measure it, and also measure it in all different, in a more formal way. Yeah, even though we have shown you how to do an internal antenna and to match it, we do see that if you are in the really low volumes, that means if you plan to send 1,000 of your products or 500 of your products, we do recommend using an external antenna, because we do not think it's business-wise smart to make your own antenna. But in cases where you do need a bit higher volumes, you do want to have the cost. I'm not sure what the upper antenna here costs, but there are some dollars, I would imagine. And going down to the helical coils, you will get that drastically reduced, because a lot of low cost Asian companies can make the wire itself. And this will be suitable for the range of 5K to 200K of your product, we believe. If you go for like 1 million of your products, then you probably can afford to hire this antenna engineering company to do your antenna the theoretical way. So in case that's your goal, to sell millions of products, we do think that that might be business-wise advisable in that case. Yeah. Also, I want to say that this presentation, we have intentionally avoided the theoretical things around the antenna. And that's not by accident, that's by intention, because there's a lot of technical terms regarding antennas, everything from VSWR to Smith charts and reflection coefficient, and a lot of technical terms that we could have used, which all the antenna engineers probably miss when they hear this presentation. And that's because this is not intended for the RF engineers with all the technical background. This is more intended for the non-RF engineers to make the antenna. But in case you want more info, you can find it on our website. You will find this webinar also as an application note, which goes a bit more in detail. It also suggests the antenna to start with and goes through the steps a bit more in detail. Also, you can find our MBUS user manual there, which guides you how to actually use this antenna feature. And we also have a white paper on selecting the antenna, where you will find a good reference starting point to make an antenna for 169 megahertz. Yes, then we have come to the Q&A session. So I will leave the word to Anders again, and I will have a look at the technical questions in the meantime. Okay, take it away, Anders.
Yeah, thank you, Ørjan. Thanks. Good presentation as always. So thanks a lot. One question I had actually here is, as you have done this several times, how long time do you spend to tune an antenna? Is this a process of minutes, hours, days, or how long time does this take for someone who knows what to do?
If you have if you can set up for one day, you could basically tune this antenna up in one day. Yeah, one day I would say you would be able to tune the antenna up. But of course, you might be if you have chosen a bit more antenna, which is not the reference design we suggest, it might be slightly more. But I would say one day.
Okay. All right. Thank you. I just wanted to sort of size up the problem and the effort here. So we have a couple of questions on the chat. I will read them out there, and I think they are kind of for you, Ørjan, that I see right now. So Antonio is asking on the test mode 7, quoting that the user manual 1.74 says up to test mode 4. So where is test mode 7 is the question.
It's in user manual revision 1.75.
Yes. So so it's a new feature that we're just launching. It was a hidden feature earlier, but we have just launched this to the outside world. So that's why you don't find it in the old user manuals. But now it's a supported feature where we also are bringing out content on the web on this feature, and the user manual is updated accordingly. Simon comes in with a question here. If adjusting the matching changes the required antenna length, why don't change the order? Why don't do the tuning of the network first and then do the length of the antenna?
Yeah, that's a very good question. That's because we often see that the antenna length is the big coarse tuning. So that means that has a very large effect. And if you have the wrong length, that means you will typically not be able to get any good matching done at all. So it's much, the antenna length is a much more coarse tuning. So it's not a fine tuning, but it can move the antenna quite much. We do see that we typically make the antenna maybe 1 to 2 centimeters too long when we first produce a batch, and then we cut from there. And if we miss by like a centimeter or 2, then it's very difficult. You won't get any sense by matching it at that point. So that's the reason.
Okay, thank you. Simon also had a follow-on question here. So if this was a hidden feature in the firmware, can we say from which firmware revision it is actually available? Do you have that from the top of your head, Ørjan?
Yeah, I think it's firmware revision. Yeah, so it's not. It hasn't been out there that long. So no, this is in the revision 105, I believe, of that firmware.
Okay, so we'll get back, Simon. If you can send us a separate email on that one, we'll confirm that. But as I said, from the top of the Ørjan's mind here, it's revision number 105. Mark is asking, is this supported also in the firmware for tiny mesh modules on 169?
At the moment, not. So that's yeah. At the moment, it's not supported. We don't have any committed plans to have it included, but of course, it's possible. One option is, of course, to have a module for MBUS 4 and tune the antenna with that one, and then switch to other protocol later. Because yeah, that's the one way to get around it.
So so we haven't implemented the tiny mesh now. We would need, like we always need to do, is prioritize our efforts here. So given the right business case, we can for sure implement it on the tiny mesh module as well. We have used it on MBUS because that's where we've seen the need for this tuning from our perspective and our customers in the first place. I have a question from Sergio. How about products that may be installed on a wall or on a metallic lamppost? The proximity or ground of metallic parts affects a lot this frequency. Should we do the matching for every type of location, or is there any rule of thumb to take that into account?
Yeah, that's quite a big question, I would say, and of course it depends all on the product. So this is the rule of thumb we see is works very well for us through several designs, and of course it depends how where these metallic pieces are related to the product. If they are normally, if you have a helical on the ground plane, that means if you have the metallic very close, then it will change stuff, and it will basically, metallic close to the antenna will capacitively load the antenna and make the impedance very, very small, and that means you have more work to do with this matching than you would in a case where you don't have the metallic. But again, it's a very complex question, so I would say Sergio can contact us on support and we can discuss a specific case there in case he needs to. But yeah, in case you have metallic casing very close to the antenna, that makes it quite much harder. Yes.
So just for me then to clarify, how in the 169 megahertz world, when is something close? Well, how many centimeters or meters away would you say, as a rule of thumb now only, would be close?
Yeah, anything which is like 5 centimeter would be far away. If it's 1 centimeter close, it's definitely close. So the limit is in somewhere in the range of 3 centimeter where you come into the close area, I would say. That's just a rule of thumb. Okay,
thank you. So Ahmed asked, is it feasible to implement PCB 169 megahertz on antenna for gas or water meter products?
Yes, of course you can implement a PCB antenna. The challenge is if you want to make a PCB antenna as a quarter wave, your PCB trace has to be like 44 centimeter long, which is not very practical in most cases. So you need to make it like a meander. That means you have to go like a snake back and forward to make the antenna, and that will make it again more closer to a helical again when you make it like a zigzag or pattern. But it is possible, but it do requires a lot of space in the X and Y axis. So the difference between, if you have a product where you can have a large area but not that much height, that is a possibility. If you can have more, if you can have height but do not have the X and Y area, but you can do more in the height sections, we do recommend the helical.
Okay, thank you. Vidar Hansen's coming in with a question here. What about the design step going from a quarter wave antenna to a helical? And what about the diameters here?
Yeah, so I would recommend going to our antenna selection guide or the application notes, where we have some reference suggestions on where to start. So basically it's about how much room you have. If you have like a 4 centimeter height, then you have to make, then it's let's say on the limit to what you can do. If you have 5, that means, or 6 centimeters height, that means you can make it a bit more narrow, the diameters, and rather increase the heights and get a bit more performance. So again, size matters, so the bigger the better.
Okay. Question from Goodwin. What is the value of the other passive components in the matching network?
Yes, so that was the point, Goodwin, that we do with this antenna, we see that we can make it work with only one component. So that means the others, of course, the capacitor there in the middle need to be like a serum or something to get passed through the signal, and the other will not mount it. So we do recommend having the other components there, so you can do, in case you get into some trouble, you could also try to do those components, but in our cases, in our reference design, we only end up with matching with the one inductor.
Okay. Thomas asking, how much loss should you expect for an antenna that you mentioned today in dBIs?
Yeah, so I would expect you to get from in the range of -7, -8 from that, in that range, -6, -7, -8. Depending on a bit on how big your ground plane is and stuff like that.
Okay. All right. Lars asks, do you have any experience in dual band antennas for 169 and 868 megahertz?
The simple question would be, we know we don't have a lot of experience in that. Of course, they are very different in frequencies. So again, having a combination of 10 of those two would for me, yeah, again recommend going through a antenna design house, basically, because that would be a advanced feature.
Mm-hmm. Okay, thank you, Ørjan. I think we have run out of questions, and that we have responded to everything that comes out. So with that, I think we will close the Q&A session. If there's anything else coming up for anyone or anything, just send us an email on to sales@radiocrafts.com, and we will take a look at it and respond as much as we can. So with that, close that. Also remind you that you have the offer on the development kit. This is actually including then the product and development kit that Ørjan has been mentioning today. So you will find a note there what that is in terms of the part number, and also where to find and place some orders on that one. So with that, I would like to thank you all for attending this webinar. I hope we brought some value to each and every one of you. As I said in the beginning, this is a series of webinars, so keep checking your mailbox for the next webinar. What I believe we should do that we haven't done is we haven't posted the schedule of or the topics of the webinars that are coming up. So Nereus, you and I need to do some work here. But for now, please check your mailboxes in terms of the next webinar coming up. So thanks a lot for participating. I hope you had some good fun. I will also say thank you on behalf of Nereus, who don't have access to his microphone right now. And Ørjan also sends his thank you here through me. So with that, thanks a lot, and have a good continued Friday.